Okay, so based on what we did last time in the last video, we did things like this. We made a node class consisting of two member variables. You can insert constructors and various functions for a node class if you want to, but we are going to make a linked list class consisting of node objects. Um, so So that's what we're gonna spend this dot 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 here that I have currently. We're gonna spend the majority of, I mean, all of the remainder of the content on linked lists. We're gonna spend it filling out these braces, filling out this definition of a linked list class, and of course coming into the main function and creating linked list objects and testing the functionality of these methods. Traversing a linked list, creating a linked list, inserting elements in a linked list, deleting elements from a linked list, where these elements are going to be nodes. It's not just going to be some data. That is the case for creating um, creating an array. The elements are just the data of interest. There is no need to store the memory addresses, and that's a deficiency in linked lists. The fact that you have to it's a deficiency of this data structure. The fact that you also have to make space for the addresses of next of other nodes in the list, whether they are previous and next nodes, as is the case for a doubly linked list, or just a singly linked list that contains some link here to another element, to another node. Okay, but based on what we did last time, um, it should be within our ability to answer questions like this. Look at a diagram of a linked list. We have a first node, a current node, which we will probably be using to iterate through this linked list. There's a last node, and a matching question like this should be within our capabilities. First node arrow info is equal to whiskey. So this is a matching question that I made. Current node arrow info. There's the current node. The info it contains is tango. This is straightforward stuff. Last node arrow link. What is this? It is the null pointer. Okay. Null. Last node. So last node contains the address 0x2. Okay, so this should be doable. Remember last time if we printed a node, so what did we see if we printed first? Can we print first? No. Can we print the address of first? Yes. So this quiz should be doable. Let's see. I use alternative syntax, head and tail here, or alternative language, head and tail. That's similar to first and last. This is a pretty simple example, this diagram. The question number 2, both of the diagrams are simple. It's just, I'm talking about the questions here. I don't chain the operation many times here. What do I mean by chain? It's just a term I make up. Head arrow link, arrow info, head arrow link, arrow info 1.618. Okay. We should be hopefully pretty comfortable with this terminology. I also give the possibility of an error here. An error would be occurring if we step beyond the null pointer, for instance, or if we try to print the, let's see, if we say link arrow info link, info doesn't have a link. Info is not a node, it's data. It's a primitive. It is these doubles in this case. A double data type doesn't have a link to a next pointer. Okay. In the instructions, I was assuming that this is declared as a pointer variable in that quiz. So now you can print first. That was my mistake. And not a mistake, strictly speaking, just two different ways of doing the same thing, a similar thing. And that is mentioned in this addendum to last time business. You can change this code and declare a pointer to the first node. And then you update and you have to use the arrow operator here in order to access the member variable. And here, initially, first arrow link is equal to null pointer. Let's see, let me bring up the diagram that I made last time. Maybe I named it. Maybe it was this one. Yes. Okay. 42, negative 23, and 76. 42, negative 23, and 76. So I was playing around here with a circularly linked list, but this is the way that our linked list looked first, and there was no, it wasn't a doubly linked list. That would be a doubly linked list. Okay, so just to rewrite this using pointers, declaring pointers to nodes. Okay, node star second, second arrow data, second arrow link equal null pointer, and then I update first link to point at second, the address of second, except, and this gets to, why would we declare pointers to nodes rather than just node objects? The use of the ampersand can be avoided in this case. First arrow link equals second, so second is going to be the address of the second node. Okay, so node pointer to a third node, third arrow link, third arrow data. Now update seconds link. Initially, seconds link is pointing at the null pointer because, and what I'm talking about here is we've created a second node, and at the moment there's no third node. Whenever we get to this instruction, there is no third node, so second arrow link should point to nothing. Nothing is coming after it. But after we insert a third element, after we create a third node, we should update seconds link to point at the memory address of the third node, like this. Okay. Okay, so now that also gets to this bit of operator precedence business that I mentioned last time. Using this, if you declare first as a not a pointer object. Let me just create a first node here that is not a pointer type. It's an object. Using this syntax, this has to do with the operator precedence, the dereferencing operator, and then you use parentheses, and then you can use the dot operator. But if you don't use parentheses, the order of operations in C++ results in this not working. So they came up with the arrow operator as an alternative. Hopefully you can see that this right here, I've made a new variable name, but this right here is taking the place of this, or yeah. So in an effort another reason to declare the nodes as pointer types is this kind of looks unpleasant on first dot link, arrow data. Instead of that, we can chain the arrow operator. And so the addendum that I mentioned in my slides here, it might sometimes it can be nice to declare nodes as pointer types. It can be a bit confusing, which is why on the quiz just there I flubbed around a little bit. You have to be careful if these diagrams is head the address, or is it a pointer type? Is it a pointer to a node, or is it a node? So you just have to be careful with that. And sometimes textbooks and people writing programs can choose one of those two options, and it can be a little bit confusing. Okay, but the error messages are generally pretty comprehensible. So it says expression must have object class type. It must be an object, in other words, but it is a pointer type. And if we go in the opposite direction, it says the arrow operator was applied to node instead of to a pointer type. So we will want to make node a pointer type, or first a pointer type, a pointer to a node object. Okay. Let's start filling out the linked list class. And let's hide the rest of this. Let's hide this business in which we gain some basic familiarity with the linked lists. So in my slides, I mentioned we want to make methods such as these, and all of these methods have some complexity. We could go to CPP reference. We could look up a standard forward list. That is a link, what C++ in the standard library calls a singly linked list. It's on here somewhere. It is implemented as a singly linked list. So remember hopefully we're okay with the difference between a singly linked list and a doubly linked list. We have these functions such as front. Accessing the front element has constant time complexity. That is big O1, or I would prefer it if it's a big OC constant, but big O1 is usually the way that is represented. Constant time complexity. Doesn't matter if the linked list consists of 100 million elements or 10 elements, getting the front element is going to take approximately the same amount of time, for assuming the same machine is used and the load isn't varying on the machine. Okay, these other methods, clearing the list, push front, so push an element to the front of the list, is constant time complexity. Insertion, so where do we insert after? Yeah, insert after. Constant time complexity for these two flavors, 1 and 2. This 1 and 2 is referring to using this overload of or these two overloads of the insert after function. Okay, well, we're going to write some of these methods. So I am going to use templates here, and there are benefits of using templates. Of course, generic programming. So template type name T info. I guess I'm switching my variable names here. So, all right, node T star link. Okay. Node of type T link. It's a pointer. Of course, it's a pointer. All right. And it's not previous in this case. We're only where this is a singly linked list node class. We could we wanted to make it a doubly linked list. We could say previous and current. So pointers to the current node, excuse me, next. So next and previous. That would be for a doubly linked list. But for now, we're just going to simply call it link, as in a link to another node. Okay. So once again, using templates to allow the main program to make a linked list of any type that we like. It could be song objects, which is something I have an assignment on. Except song is not defined at the moment, but that'll, I'm talking about just making a struct called song and string artist name and string song name and int song length, something like this. And then we could, so that would potentially be a neat thing to do. Okay. But if we don't use templates, then this will be a problem. If I comment this out, then all of a sudden may not have a template argument list because I didn't use templates here. A template. Okay. So node type T, node type T, front, back, next. So there's no need for next here. There's no need for data because the info, that is the data, and link or next are contained in the node struct. So the linked list class is going to have a front node and a back node, or let's say first and last, just to stick with the what I used in my slides. Maybe we only have first. Their choices here. Okay. Okay, a constructor. So a public constructor. We want to make these member variables private, perhaps, so that the main function can't do unfortunate things to those member variables, like going out of bounds and deleting them, maybe. Okay, so a linked list constructor doesn't, default constructor doesn't take any arguments. We should set first equal to the null pointer and set last equal to the null pointer. I say we should, but there are options. What is this code doing? Set first equal to null pointer, set last equal to null pointer. That is, and is there any data, okay, in this? We have a first and we have a last. And I haven't mentioned any data yet. So what I've done with this code right here is set first equal to null pointer and last equal to null pointer. Excuse me, what this code is saying is setting first arrow link equal to null pointer. So first equal null pointer and last equal null pointer is, it's just a setting. It is in terms of a diagram. It is this. So nothing particularly interesting going on here. First equal null pointer, last equal null pointer for the default constructor. And it initializes the node count to 0 because there are 0 nodes here. Of course, we will add nodes. So we're going to write a function called add node, or something synonymous with that. Okay, so print node info, return number of nodes, a print function. Print, shouldn't take any arguments. Print the node info and return number of nodes. I guess maybe two different functions. Print and length. Length shouldn't take any arguments. It should return an integer, not a double, because there can't be fractional values for the number of nodes. Return node count. We made that a member variable, so that's similar to a getter function. Let's see, where did I declare node count? Excuse me, I forgot to add that as a member variable. So yes, we have first, last, and node count. Maybe not mandatory to include this member variable, but it can be convenient. So maybe it's worth the space. And we're going to increment this every time we add a node. At the moment, we have 0 nodes for this default constructor. Okay, print function. Let's see, node star current. And we say maybe a for loop. While loop makes more sense maybe in this case. While current is not equal to null pointer. So what does this mean? While current is not equal to the null pointer. So if the current node if currently we are pointing to this node, then current is not null. But if we say current arrow link, then the value is the null pointer. So that is indicating that we have hit the end of the linked list. So while current is not equal to the null pointer, we say cout current arrow info. And we increment current. It is a form of incrementing. We say current equal current arrow next, or current arrow length rather. Okay. So not seeing auto completion for these. Let's see, current arrow, current dot node. Excuse me, that's my problem here. Node T. Now if I type, we see info and link. Okay. So this statement right here, it updates the position of current. If we start out at the beginning of this linked list that we got into last time, that we wrote the code for last time, if current is a node that points at the first, that is pointing at the first node, how do we step forward? We follow the link. We say current equal current arrow link. And let's test this. Well, we will certainly test it in a bit. This is a traversal of a linked list. This print function is going to traverse the linked list. Okay. And there is a very important statement that I'm missing here. Current, this declares the node, and we want to say current equal first. We want to start at the beginning of the linked list. We could also start at the other end. That would maybe be a bit of a strange thing to do. We wanted to traverse the linked list in the reverse direction. Okay, so at the moment, we only have a linked list default constructor that doesn't insert any nodes. So of course, we want to insert nodes. Insert first. I think insert first as in insert at the first, insert as the first element of the linked list. So that is going to be a function we would like to have. Insert first, open up a function definition. The return type, should we return a linked list? Should we say void and we're just updating the list? Do we need elements? We definitely, or do we need arguments? So data to insert. We're inserting at the beginning of the linked list. So we don't need to specify a position here. Something like this wouldn't necessarily make sense in this case. How do we do this? Insert first. Picture's worth 1,000 words here. So we have a first node and a last node. That's whenever we create the linked list. We say linked list. Let's use integers here. Call it nums list. So this will create a linked list of nums using this default constructor. The node count is going to be 0. So let's insert nodes. Let's say nums list dot insert first, and we'll insert the element 3, the integer 3. And now if we say cout nums list dot print, we would see the value 3. And only the value 3. And there's a problem here because we haven't written the insert first function. And we also haven't specified the return type of print function is void here. And we also need to not be silly like this. Okay, so we print nothing because we left the insert first function definition empty. So node count is going to get incremented by 1 in this function definition because we inserted a node. So node of type T star new node equal new node of type T. Then we say new node dot info or arrow info equal data to insert. Okay. And maybe at this point we could go ahead and increment the node count. And we inserted this, so we've made a new node. This is what we have. We have new node. We have something called first. It's a node type, a node that takes elements of type T. So it has space for data and a pointer to another node. That space isn't currently occupied. So we just made a new node consisting of the value 3, I think we said. It's arbitrary. Okay. We made a new node, but we want it to be the first node. So maybe this isn't the best way to go about this. Let me take a look at my slides. New node equal node of type T. Okay. And new node arrow link equal first. All right. So what does this do? New node arrow link equal first. So this is link here. The second box is the link. So new node arrow link points to first. So let's insert an arrow here. So that is what this line of code does. New node arrow link equal first. And first is a member variable. So first is the null pointer. The address of first is the null pointer. And are we content with this? Is this all that we need to do? No. So first equal new node. What is this accomplishing? First equal new node. Okay, let's not over analyze the meaning of this. First equal new node, we'll step through it and step through the program. We'll step through these instructions line by line in debug mode in a bit, and we'll get some insight into what's going on here. As far as the diagram is concerned, maybe it's a little inobvious what happens when we say first equal new node. First is a pointer type and new node is a pointer type. So the address of the new node becomes the same, gets assigned to the address of the first node. The new node is becoming the first node. I'm not quite sure how to show it with a diagram. I mean, just an overwrite here, so to speak, but we want to hold on to first because it enables us to keep track of what the first node is, and we also want to hold on to this member variable last, which is because we want to be able to know what the last node in our linked list is. It's convenient, as we'll see. So one last, so last is out of the loop right now. So one last point, sort of pun intended. We need to update we need to link the new node to the last node. So if last is equal to the null pointer, which it is right after the default constructor gets called, it's equal to the null pointer. We perform that assignment operation. Then we set last to the new node is both the first and the last node. So we set last equal to the new node. Okay. So let's make a linked list and insert a few elements. Let's just insert one element for now and comment out the print function. So we'll set a breakpoint here and step through this. And maybe we can make some sense of our diagram as well. We can do a follow along with our diagram as well. Okay, so we have created our linked list on line 82. Let's see, I don't think memory will be particularly helpful here. I think it'll be okay just to look at the local variables here. Okay. So after we create the nums list that called the default constructor right here, first equal null pointer, that's that. Last equal null pointer, info and link, there's nothing in there. We didn't say first arrow link equal anything, first arrow info equal anything. So unable to read memory appears. Okay, we're not talking about the print function, so let me collapse the print function. The length is straightforward. The node count is initially 0, and there you can see node count is 0. The insert first function, so I set the breakpoint right here, so let's step into that function and see what changes occur to first and last. We're also going to get this new node. Okay, so new node is not yet created. Okay, but we step and it gets created and it has an address that's returned. This is this heap allocation of memory. New node gets created. It has an address. Info and link aren't yet established, but I inserted the value 3. We're also going to increment node count. So let's step and the data to insert is 3. So new node arrow info, after I execute this, this is going to get updated to 3. Okay, and the link is going to get set to the address of, it's going to get set to first, and first is the null pointer, so the link is going to be null pointer here. So null, now first equal new node. Now first, I think maybe we won't see it in the locals here, but first its address is going to change from null pointer to this address, the 186834C, etc. So we'll see that change. Now the address of first is the it shares the address of new node. Okay, and if last is equal to null pointer, which it is, we give last the same address as well. So straightforward. Last has the same address as the address of the new node and the first node. It's the first and only node we've inserted. So that's the end of that. Now we hit return 0. We're not going to print. So nothing particularly interesting happened whenever we only inserted a single element. So let's insert first the element 52. And what will that look like? Well, so let's stop and we'll rerun in a minute. But can we think about that first? 52. Can we draw a diagram? So now first is going to contain the info3, and its link is going to point to the null pointer. It's a bit confusing, I suppose, but this node is both the first and the last node. And it's going to point to null pointer. I'm not sure if we did that explicitly, but now we're going to create a new node, and that new node is going to contain the value 52. And what we want to do in this insert first function, is we want to move this and put it here. And set it to be the first node, and set the node containing the value 3 to be the last node. So will our function do this? Let's take a look at the function definition before we step through. We create a new node, this new node containing some memory that is a heap. It's a memory address generated on the heap. I haven't talked much about the heap. Maybe in the future I will. So the node's info is equal to 52. That's what's represented in the box there. The link is going to point to first, where it contains the address of the first element. So here's link. So we point it the first node. Then we set first equal to new node. So this is both first and new node. And the last node is now the second node in the list. And is last equal to null pointer? No. So we're not going to do this. We're not going to call the first node and the last node and the new node. So I think it's that straightforward, this function definition. Let's step through it and see what happens. Set a breakpoint. And this will be a good stopping point for this video, because I think this video has gone on quite long. So let's yeah, that's a good breakpoint, I think. The nums list consists of one node. First and last are the same address because we've only inserted one node containing the info 3, value 3. Link is equal to null pointer. And I think that's implicit. I was asking about that a minute ago, whether or not this points to null pointer. Yes, it does. I think it's auto initialized. So link is null. Okay, there is no previous, so we don't have to think about does we don't have to think about do we have another, do we have a previous node that we're not using a doubly linked list here? Okay, so insert first. Let's step into that function. Okay, we create a new node on this. Now we increment the node count, which was 1 previously. So now the node count is going to be 2, as you can see. The new node has some memory address, uninitialized. Yeah. So now link equal first is going to get set to the address of that first node, the node containing the value 3. The info is 52. That's what I passed in here. Okay, so link new node arrow link equal first. So we could open up memory and see that let me do that. See that the address of first node is what we're seeing right here. I think it's straightforward. Okay. I mean, this entire function definition is pretty straightforward. I'm not sure if I can explain it in more detail. Is last equal to null pointer? Let's see, no, it's not. Last arrow link is equal to null pointer. Yeah. Step, and we hit the end. Okay, so let's see if our print function works, and that'll be a good stopping point. We just want to see the nodes, the node values, the data contained in the nodes, which is 3 and 52. And we want to see it in the order 52 and 3, because 52, we didn't say insert last, we said insert first. So let's take a look at that print function definition. I think that there are no bugs in our insert first function. We set up an iterator node, and we start at the first position, and while current is not equal to the null pointer, another way to write this is while current arrow I was about to say while current arrow link is not equal to null pointer, but this is there are different ways to do it. Okay, so yeah, let's set a breakpoint in this also, and this will be again a good stopping point. And bring up local variables. Okay, so 2 nodes looks right. We inserted 2 nodes. First contains the value 52, and the link to the last node, in this case, the second node. Notice that the link contain the memory address is E2600. The address of last is E2600. Okay, that makes sense. Last contains the info of 3, and its link is the null pointer. So I think yeah, everything looks fine from the linked list perspective, but does the print function work successfully? Let's take a look. We haven't printed anything yet. We're going to set up a current node. I don't think there's anything to be gained by saying equal new node .t at this point, because we're right about to set current equal to the address equal to first, which again, these are pointers. I keep on saying the address of first. It's a bad habit. Maybe it makes things confusing. Okay, so step current gets set to first. Okay. So this object is a linked list. consisting of two nodes. The object on which the print function got called is the linked list of two, the nums list, linked list of two nodes. Okay, so current equal first, current equal that memory address. Yep. And is current the null pointer? No. So we will execute this. So we print current arrow info. And what is current? Current is a pointer to a node. So it has this memory address, and the info is 52, and the link is the link to the next node. And okay, so step, and we print current arrow info, which is 52, and we step along the chain, current equal current arrow link, and current's link points to the node containing the value 3. Okay, now current, the link of current is going to be the null pointer, so this loop will only execute twice. So we printed 52 and 3, and then this while loop is not going to execute. And we're going to step back to the main function and return 0. Okay. That in the next video we'll get into, so this is my alternative testing. We're going to add an insert after function, so an insert after a certain node. So that gets more interesting, and that's a nice thing.